So today we will have a second lecture by Vaughan Jones, and will certainly be as brilliant as the first one we had 2 days ago. And the title today is von Neumann algebras. Oh, sorry, that's his broad field, knot and polynomials. But the title of this lecture is Subfactors, Loop Groups, and Conformal Field Theory. Please, John.
All right, well, thank you all for coming back. Give these talks and lots of people tell you afterwards what a great talk it was, but the real proof is how many people come back for the second talk. So we'll see. So today I want to talk about something, tell a very different story from last time, and it won't be obvious till the very end what the connection is between the two stories. In some sense, today's story is a little bit more advanced in that I will allow myself to freely use words like representation and Lie group and Hilbert space, whereas I was deliberately avoiding anything that advanced in the previous lecture. But I think I've probably scared off all the students by now anyway, so it should be all right. One thing that I feel guilty about, as always in my last talk, and in every talk I give, is I forgot all of the attributions. I just didn't really tell who had done anything. And, the guilt is overcoming with two names, so I just want to add two names that I should have. The first one is Greg Cooperberg, who was a student, did his PhD at Berkeley, and now he's at Davis, and Lou Kaufman. So. The first attribution should be that Greg came up with essentially the same sort of formalism as I ended up with on Monday, and Kaufman is somehow everywhere dense in the picture. So, or let me add a third name in case at the end I forget to give the attribution. The main person whose work I'll be eventually getting to today is Anthony Wasserman. So hopefully at the end I will cite a theorem due to Anthony, and it's a big theorem. I think it's a very beautiful result. It's by now quite old, but I just spent a whole semester giving a course on this paper of his. And it's very nice, all kinds of ways. So yesterday, so I guess on Monday, I gave a talk which gave a somewhat tongue-in-cheek definition of the word subfactor. Which had its advantages. The advantage was that I could stay elementary and somehow combinatorial, but the disadvantage is that now I'm stuck with that. So it's a problem. So I have to get over that somehow today and tell you more or less what is really meant by the term. So let me just remind you of what I called a subfactor last time, and then I'll translate that. From that, I'll construct what a real, genuine subfactor. So there's no great mystery. A subfactor is a factor is some kind of algebra of operators on a Hilbert space, bounded operators on a Hilbert space, and a subfactor is a smaller one. So that's going to be what I'm going to construct from the data that we dealt with on Monday. So on Monday we had this idea of a planar network labeled planar network. Where we had some kind of planar configuration like this. I called these labels, I think I called them samba schools or something, but I'm not sure that anyone really realized what I was saying, and that it was actually supposed to be a joke, because I don't think anyone laughed. Anyway, today we'll forget about samba schools. These things are now going to be called labels, all right, a bit more prosaic. So that's an example of a planar network, a labeled planar network. There's some set, possibly infinite, of labels, and planar, and you put them in little boxes, and you tie these boxes together in any way that you like, such that the strings, these are the strings and these are the boxes, the strings are not allowed to cross. That's what the word planar is about. All right, and I said the tongue-in-cheek definition of a subfactor was that it was an invariant, which I'll now use the letter Z, of labeled planar tangles. So given some set of labels, a subfactor subfactor in quotes is an invariant. So invariant simply means to every labeled planar tangle you get a number, and right, to every, and it doesn't, you're allowed to do any kind of planar isotopies of this. So if you sort of, if you decided to that should be the same thing. Move everything around in a smooth way. Okay, and there's just a couple of axioms. The main thing was that to introduce another concept, which was a labeled planar tangle, which was simply, if you like, a tangle in the knot theory sense was a knot with boundary. A labeled planar tangle is a labeled planar network with boundary. So a labeled planar tangle, let me try to get some colors in here, might help. Oh, not that. That's a bad color. Let's try. So it's as if I was drawing, so there's maybe some R's and some S's. I start off drawing a labeled planar network, but then some of these strings go to the boundary. Okay? And I can think of the boundary, if you like, as being part of another big, just like that. So, and the point about having one of these invariants, Z is supposed to recall for you the partition function from physics, is that you can define some kind of inner product on labeled planar tangles. And this is simply, you take one of these labeled planar tangles, it has a certain number of boundary strings, and then you have another one, S star. Actually, S is a bad letter, isn't it? Because I used it for these, so T prime star, and this is Z of T. And it's, sorry, this is the inner product. Star just means mirror image. All right, now with this data, we had some axioms, and the axioms, the main one for me is that this form is positive semi-definite. So when it's, of course, we have to linearize everything, take linear combinations of everything, then we can talk about it being positive semi-definite. And also the quotient, which we're going to call Pn. This is a new letter, which is the linear space of all labeled planar tangles over the kernel of the form. This is with n boundary points. This has to be finite dimensional. This was the other axiom, dimension of Pn. And as Alberto pointed out, it's only my obsession that puts the first axiom, the positivity, as the first one, and this one as the second one. In some sense, if you get these things being finite dimensional, you're in business. Okay. So that just about sums up where we got to last time. let me emphasize right away something that wasn't clear because I didn't give any examples. I didn't know how I got away without giving examples. But there are squillions of examples of these things. The theory of this theory strictly contains all groups, finite groups. So that is to say, given a finite group, I can form one of these labeled lots of thingamajigs such that one of these so-called subfactors, such that the finite group can be completely reconstructed in all its glory from that object. It also contains compact groups. It also contains quantum groups. And here's a surprise, it also contains finitely generated discrete groups. Okay, so all of these subjects are actually strictly contained in the theory of these labeled planar tangles, just by giving examples. And I could spend the rest of the lecture just giving some really neat examples, but I want to tell a different story. There's also a connection with conformal field theory, and it's sort of known that every conformal field theory will give one of these things, and the other direction is a very, very, very interesting somewhat open problem. All right. So that sums up and says a little bit more than where we were last time. Just take it from me. There's lots and lots and lots of examples with very, very rich combinatorics and analysis. Right. So now I have to make a construction because I want to get these subfactors as they're supposed to be. So now I want to construct a subfactor from one of these, what I've called one of these z's, one of these pseudo subfactors, partition function. I want to construct a subfactor as, completely honestly, as an algebra of bounded operators on a Hilbert space. So I've got to start by constructing the Hilbert space. Okay? Well, I'm going to do this in a two-step procedure. I'm going to first of all construct the algebra. From the algebra, I'll construct the Hilbert space, and then I'll complete the algebra to get a factor. So we start with just an ordinary algebra, no analysis, and this is the one that I want to define. So I have to, algebra is a vector space together with associative multiplication. So here's the vector space. It's going to be, this is not the one I intended to use, but in fact this is better in some ways because the things are actually going to be true, as I say about it, rather than, true under certain circumstances. So here, algebra. Let me give it some here. Well, as a vector space, it's going to be the direct sum equals. So the data is, I'm given one of these thingies, these invariants of labeled tangles. So therefore I can, with satisfying the axioms, so I can form this Pn, which is this finite dimensional vector space, and then I'm going to add them all up over all n, but I'm just going to have a slight shift. I could do it without that shift, but you'll see the reason for that shift in a second. So an element of this algebra is going to be a bunch of linear combinations of labeled tangles with n boundary points for n equals 1, 2, up to some 50 or something. It's going to be an element of the algebra. So I have to tell you how to multiply them. That's the main thing. And the multiplication is just a question of drawing a picture. So if I have x and I have y, and x is in Pn and y is in Pm plus 2, then I've got to get another element. It's got to be in here, and it's actually going to be in xy is going to be in Pn plus m plus 2. And here it is. I take x. X, remember, is a labeled tangle, so I can draw it like that, where I've deliberately put this string here, one of the strings there, and so there's n here. And y is like that, with its m Okay? And then I just simply join them, the two tangles together along these things. So this is, again, this is a labeled planar tangle with n plus m plus 2 strings. Okay? You can easily check associativity, and this makes this thing into a graded algebra. And there's a star algebra coming from mirror image. And it's a unital algebra. There's an identity. If you want to see the identity, then there's the identity. This is in P2. It's that tangle. It's basically reflection. Yeah. If you take X and reflect it like that. I'm trying to, there's a few words to be said, but I'm trying to avoid saying them to save time. All right, very good. Now I'm going to tell a lie, just to say, also to save time. The truth behind the lie is a really interesting story. It involves random matrices, large n limit of random matrices, and if you want to hear it, come along to my talk tomorrow. Yeah.
Is it obvious that this goes down to the kernel? That this goes down to that quotient? That this multiplication is actually well defined?
It's a little exercise. Yeah, you need to check something, but that's not very hard. It's just planar stuff. I agree there's something to be checked, but that's one of the things that certainly works. I just went through it in my head. Okay, so now I want to get, so that's algebra. It's nothing but algebra. Right? I've got this algebra, infinite dimensional algebra. Now I want to put some analysis on, so I want to turn it into a Hilbert space. And what I'm going to then talk about is the so-called GNS construction. Gelfand, Neumark, Siegel, and that's a sort of machine for taking algebras and producing von Neumann algebras, so we're going to have to get a Hilbert space. And the Hilbert space is given by putting a trace on this algebra. On, what did I call it? M. And here it is, the trace of the direct sum of xn. Remember, an element of the algebra is a whole lot of labeled tangles, is equal to z, this is the data, of x0. We forget everything except x0. And then to apply z, we need to have something without any boundary points. It's got to be a network, so I simply tie x0. So this is x in. So this is. It's the first one. The very first one has two boundary points, and I tie them together. Okay. So I said this is the lie, but the real story is much more interesting, and it's got to do with random matrices and come along. Anyway, the point is that once you have this kind of thing, this GNS construction takes over for you. And I want to say what it is because I'm going to use it again in a different context shortly. So now I'm going to put an inner product on M. And it's simply going to be x, y equals the trace of y star x. Okay? This is a definition. And now, because we've quotiented out by this kernel, this is a positive definite linear function. So we have the trace of x star x is actually greater than, not equal to 0, for x not equal to 0. So M becomes a pre-Hilbert space. And we let M bar be the completion of M. So that's a Hilbert space. And let me write that big. Okay? That's where we want to live. That's today's theatre, is Hilbert space. And then we've got one. It's the closure of this guy. M itself, being an algebra, it acts on the left on itself. Little calculation shows that action of M on itself is by bounded operators, so therefore it extends to the closure, and M, by definition, is the closure of M on the Hilbert space. Closure in what topology? Pointwise convergence, if you want to know. All right, so there it was. There was the tortuous, slightly painful construction. But believe me, when you're working in this theory, it's like that. You see an algebra, GNS. Okay, so let me just go over it again quickly. We had this algebra, star algebra. We had a trace on it. We immediately formed the inner product, completed it into a Hilbert space, and then let the algebra act on itself, extended it to the whole Hilbert space, and then we took the closure. And we got what's called a von Neumann algebra, because that's the definition of a von Neumann algebra, something that's closed under pointwise convergence on the Hilbert space. Now it turns out that this particular construction always yields a factor. And a factor is a von Neumann algebra whose center is trivial, no center. That's actually very easy to check on the purely algebraic level. You can just check by drawing pictures that there's nothing in this algebra that commutes with everything else in it. So the difficult thing is to check that when we take these weak limits, we're taking this closure, and maybe that topology is a little bit odd. And, maybe it's not a factor. Maybe there's something that comes in the center as a limit, but it doesn't. So we've got what's called a factor. All right, now to get all the way there, what I said was a subfactor. So a subfactor has got to be a smaller algebra that's also a factor, and it's visible. The point about drawing all these pictures is it's visible. We just draw, we take a subalgebra, which is defined in terms of pictures. And we call it N. So we take the set of all linear combinations of, or maybe if I don't even need that, picture the following form. This is direct sums of N, and this is N. All right, we just have the 2 points. Where was the definition of these things? These elements, I was thinking of as having N points here and one here and one here. Well, there's things such that this line, and the tangle such that this line just goes straight through and it's connected to that. Well, that's obviously a subalgebra. If you multiply, if this one went straight through here, and this one went straight through here, then when you put them together, it still goes straight through. So it's a subalgebra. Substar algebra, because if you reflect it, it's true. And this is also a factor, and so I have to take the closure of this subalgebra, and N contained in M is the subfactor. And it's a whole other story, but it's true. Let me say that it's true that you can construct the invariant of planar networks from that subfactor. Throw away everything else. Just give yourself this algebra and a smaller algebra on Hilbert space. Throw everything else away. You can reconstruct this partition function. All right, so that's the end of the last lecture. Finally got there. Now it's time to start the new lecture. So if if this was all a bit too much for you, but loss doesn't matter. New subject, and at the end I will connect them up simply by saying that some algebra of operators on the Hilbert space that I will get is going to be a subfactor, and the result will be that it's the same as this one for certain invariant of networks. Okay, maybe I should repeat that. We're going to start a new subject. At the end of that subject, we're going to come up with a subfactor acting on a Hilbert space. And the assertion will be, the theorem will be, and this is what Wasserman proved, that subfactor is actually the same as one that we would get from one of these invariants of networks. And in fact, we've already seen this one coming from the Jones polynomial. Okay. So I said here that these networks contain finite groups, but they also contain knot theory. They also contain all these knot invariants. All right, so a new subject. And, I guess this is the teacher in me, but so the physicists in the audience will probably be somewhat bored and a bit upset that I'm doing something so elementary, but it's a piece of mathematical physics that is so beautiful that every mathematician should know this. Okay? So it's physics going back to the middle or earlier in the 20th century. But it has some advantages in that it is quantum field theory. It's a little part of quantum field theory, but it's perfectly mathematically rigorous. It's beautiful, and it gets the job done. Okay? So in a word, what I'm talking about is fermionic second quantization. And I'm going to do this in a way that's completely acceptable, not only acceptable to a mathematician, but it should give the mathematician a warm, fuzzy feeling. Like this is the way things should go. It should be, oh man, obviously it evolved over a period of many years, but we'll all hopefully get a nice warm vibe from it. And it's all about the CAR algebra. So for the physicist in the audience who knows much more than this, it might be interesting to just see what, how pathetic, how little it takes to make a mathematician happy for this stuff. So we're going to have a Hilbert space, H. I'm going to give you some concrete ones shortly, but this first part of abstract nonsense just requires a Hilbert space with its inner product. And from that Hilbert space, I'm going to define a star algebra. And I'm going to define it in terms of generators and relations. And here they are. The generators are A of F. Okay? For every F in the Hilbert space, F is supposed to stand for function, as in wave function. And H is supposed to be the first quantized Hilbert space, whatever that is. I'll come back and make a comment about that. So here's the generators. For every element in the Hilbert space, there's an A of F. And then there's sort of three actions, I guess. First is, there's also going to be an identity. F going to AF is linear. Okay, so that's nice. And here's the second one is the following. AF AG plus AG AF equals 0. So all of the elements, all of these AFs, they anti-commute. Which is not very exciting. But the guts of it now is this one, which is if you take A of F, and I said it was a star algebra. So now, I don't know, physicists and mathematicians often disagree about whether it's the first or the second thing in an inner product which is antilinear. And I'm sure I've committed myself by this formula, but I'm not even going to look. So. Actually, Richard Borchers, one time in Berkeley, grabbed me in the corridor and said he had discovered that there was a canonical choice of whether it should be the first variable or the second variable that was antilinear. That was just, it was God-given. There was nothing. And he explained it to me for about half an hour. But I've forgotten. Not only have I forgotten his reasoning, I've forgotten which one it was supposed to be. So. All right. So that's the algebra. Now, the first thing I want to say about this is that it's a functor. It's a functor. it takes Hilbert spaces into star algebras, right? And why is it a functor? Well, it's a functor simply because the only ingredients that went into this presentation was the inner product of the Hilbert space. So every time I have an isometry of the Hilbert space, a unitary operator, I automatically get an automorphism of this algebra. So the unitary group of the Hilbert space goes to the automorphisms of CAR of H. So this is what the algebra is CAR of H. CAR stands for canonical anti-commutation relations, and of course you probably know that there's also a job for CCR, canonical commutation relations, and this one is all about fermions and the other one is all about bosons, but fermions are somehow easier mathematically. As you'll see, there's some nice technical properties right at the start which make life a lot easier with fermions. Okay. So it's a functor, and so this is, I can't resist. Some of you, maybe all of you, have already heard this quote, but let me say it again. It's due to Ed Nelson. And it is that first quantization is a mystery. Second quantization is a functor. Okay? So first quantization is how we came up with this H, right? And that's given by all of these bizarre geometric quantizations and L2 of S1 and intuition and guesswork and luck and so on, and the correspondence principle, which makes no sense at all. But you come up with some kind of Hilbert space for particles, and then you apply this functor to get a Hilbert space which is geared to be more for fields or, collections of these particles. So that's a physics course. I'm not going to bother you anymore with it. We'll just take it as a functor, right? It's a mapping which takes Hilbert spaces to algebras, star algebras. Okay. Now I want to make sure everyone understands something about this CAR algebra, because it's rather nice. Now normally, you see, with polynomial algebras, for instance, you always start with the 2x2 matrices, and no matter how difficult the problem that you have given yourself in polynomial algebras or in Hilbert space, you say, well, what's happening in the 2x2 matrices? So I should ask myself, what's happening for a two-dimensional Hilbert space? But in fact, the guts of it is even easier. It's for a one-dimensional Hilbert space, as I'm going to prove. All we need to really understand for the CAR is what happens in a one-dimensional Hilbert space, and we should be able to figure that out, right? So let's suppose the dimension of H is equal to 1. Okay, that means we have something generated by A of F, for F in a one-dimensional Hilbert space. So since it's linear, we might as well just take A of 1, the scalar, the 1 in the field, and then we might as well forget it, and we just have the single element A. So we're looking at the algebra, which is generated by A, and it has an identity, and then it has the relations that A plus AA is equal to 0, which is the same thing as AA is equal to 0, A squared is equal to 0, and then AA star plus A star A is equal to 1. Okay, so that's a nice algebra. We should be able to get our hands on that. And in fact, as soon as I write down one 2x2 matrix, you'll see the whole thing. If I call that A, that satisfies all of those commutation relations with the usual star on the matrices. Not only that, you'll see that the whole algebra with these commutation relations, it's spanned by 1A, A star, A, four things. So this algebra is the 2x2 matrices. And of course, the physics word to go along with it is spin. This is the Hilbert space describing a single spin sitting there with no spatial degrees of freedom. It's just a spin stuck. Nothing to say but it's spin. So it's given by this 2x2 matrix algebra. It's the observables. All right. Now there's one other thing which you can prove, which is that this functor it satisfies the following thing under direct sum. CAR of H plus K is CAR of H tensor CAR of K. So it's a functor that takes direct sums of Hilbert spaces into tensor products of algebras. So it's somehow multiplicative functor, which is what quantum stuff is supposed to be. Now you actually have to be a little bit careful here. There's what's called a Z mod 2 grading, and that would serve to just confuse the hell out of everyone if I went into it. So I'll just forget about it. Let's pretend that this is true on the nose. For CR, it would be true on the nose. Okay, so this is true, which means that once we know it, the point is that a Hilbert space has an orthonormal basis. So it's a direct sum of one-dimensional Hilbert spaces. So once we know what this looks like for a one-dimensional Hilbert space, we know what it looks like for all Hilbert spaces. And for Hilbert space, i.e. separable infinite-dimensional Hilbert space, we find that it's the tensor product, CAR of H, is the tensor product from I equals 1 to infinity of the 2 by 2 matrices. Okay? I've proved it by intimidation. I didn't do any of the details, but that's the way it has to be. Okay. Now, this is interesting because this is really interesting. Suppose we took something else called the infinite tensor product of C2 as an algebra, two-dimensional algebra of diagonal. Then this algebra here is nothing but the continuous functions on the Cantor set. Okay? So this CAR algebra is nothing but the non-commutative Cantor set. Okay? Non-commutative Cantor set. That's its role in life. That's the structure. That's because Hilbert spaces have a basis. On the other hand, I said that it has a whole bucket load of symmetries. Every time you have a unitary matrix on Hilbert space, you have an automorphism of this algebra. So all of a sudden, this non-commutative, this quantum Cantor set, instead of being like the Cantor set, which doesn't have that many symmetries, it's a very discrete sort of object. This one has beautiful flows. It has any group that you can embed into the unitary group of Hilbert space, and that includes every group that I've ever cared about, and many more, acts by automorphisms on this non-commutative Cantor set, this quantum Cantor set, okay, which we got out of this functor, fermionic second quantization. So for a mathematician, this is already a beautiful piece of work, beautiful surprise that we've got that the quantum or non-commutative world has this kind of smoothness to it if you look at it in the right way. Whereas if you look at it in this infinite tensor product way, it's a bitchy, chunky little Cantor set. All right. So let's move on to any questions? As I said, I'm telling this truly beautiful story, and I'm sorry if I'm boring the physicists because they know it too well already. Okay. The next thing I want to talk about is sort of linear functional. So remember the way that we went. So far this is all algebra, by the way. The completeness of the Hilbert space has played no role. In fact, its only role, if I stuck it in now, would be to make all the statements that I've made false. Okay? But now I can turn this algebra into some piece of analysis, and the trick will be to use this GNS construction once again. So we remember that what we did with the GNS was that thing that was first, very quick reaction was given a linear functional on the algebra, we turned it into an inner product. So I'm going to give you some linear functionals on the CAR algebra, and they go under the name of quasi-free states. And it's the following proposition. Pure mathematics. If we have a zero, so A is a self-adjoint operator on our pre-quantized Hilbert space. Okay? We start with an operator between 0 and 1 on the Hilbert space, so it's self-adjoint. This just means that the spectrum is contained in the unit interval, self-adjoint bounded operator. Then there exists phi sub A from CAR of H to C, which is completely defined by the following formula. So this is the magic formula that makes this whole stuff work beautifully. Similar formula for bosons, but so phi of, now I want to define it in any element of the CAR algebra. So I've got to write down the most arbitrary element I can think of the CAR algebra. So it's obvious it's going to be A of F's and A of F stars. The order doesn't matter because up to this relation I can commute them or anti-commute them. So here, this will be obviously A of F1, A of F2, A of Fn times A of F G M star down to A of G1 star. All right? So can anyone think of a more general element than this that I should be taking into account? No, because if you had any word on them, you can always reduce it to this. Okay, so this is equal to, this is the explicit formula. It's delta Mn. So it's 0 unless you have the same number of, by the way, A of F is called creation or annihilation depending on your frame of mind, and the A star is called the other one. Okay, delta Mn, so it's only going to be non-zero if there's the same number of creations as annihilations. And the formula for it is it's the determinant of a certain matrix, and the matrix is Fijj. Vic, yes, scream louder, Vic, absolutely. Fermionic. Right. So, that's the... Oh, good point. Good point. This is ridiculous. I better put A in there somewhere. Right. Thank you. If A wasn't there, then it wouldn't depend on the Well, all right. So what's the first example? First example, A is equal to 1, right? My formula would have been correct. But let's start even before that. Let's suppose A is equal to 0. That's a perfectly fine... sorry, I have to... Before examples, I have to do this. See, for me, it was already done. I was already there, GNS'd. See, what you can show, the first piece of magic about this formula is that it is positive semi-definite. So phi of x star x is greater than or equal to 0. Phi of x star x is greater than or equal to 0. So that's what I need to do the GNS. So remind you once again about the GNS. We're going to take CAR of H. We're going to put on an inner product, which is xy equals phi, this quasi-free state, which depends on A. Thank God, thank Raimundo for reminding me about that. CAR of H, phi sub A of y star x. That makes, now, this is greater than or equal to, it's not positive definite now, it's positive semi-definite. There may be a kernel. You quotient out by the kernel, that doesn't matter very much. And then the algebra still acts on the left. And so H sub A, this is the Hilbert space of the GNS construction. We started with H, we've applied this operator A, we've come out with H sub A, and that is completion of CAR. H. With respect to that in the product. I should no doubt put an A on it there. Everything depends on A. Okay, any questions? What about the camp here, the question camp here? It's keeping me honest.
This way, the philosophical point of view. So you started with the fermions that already have some dynamical information, and now you're adding an extra action. Oh, I see two different actions, two different Hamiltonians at the same time.
So far, I don't even have a Hamiltonian. I mean, I'm just doing a piece of mathematics. You're reading into it a bit more than it is there at the moment. I think it'll come clear to you shortly. Okay, so I assume we'll have a Hamiltonian. So where was I? Right. So I've got this Hilbert space, and I've got A CAR X on HA. So I have a representation pi sub A, which takes an element of the CAR of H, and it makes it act on, so linear maps from HA to itself. So this is bounded linear maps. Bounded is the same as continuous. And the advantage of fermions over bosons is precisely that. They're bounded. At the same point with bosons, I would get into all kinds of difficulties because the operators would be unbounded. All right. So that's very nice. We need an example pretty soon, don't we, to get our teeth around it. But I think I want to stay in the abstract for one more thing. I've forgotten what. Oh yeah, for the example, sorry, we really do need. So what happens when A? Remember, A can be absolutely any self-adjoint operator between 0 and 1. So there's the first one. Okay. Well, you'll have no problem convincing yourself that there's a kernel to this form when A is 0. It looks like you're killing everything, but in fact you're not. It turns out that in this case, the H sub A is nothing but the tensor algebra of H, in the Hilbert space sense. You take the direct sum of the antisymmetric tensor powers, you put on the Hilbert space inner product by antisymmetrizing, and then you close it up to get a Hilbert space, and that's exactly what HA is in this case here, H0. And this is, physicists call it Fock space. And that's, if you like, that's some kind of free Fock space. Now, A equals 1 is the other extreme, and here you get H sub 1, which is also a Fock space, but this time it's on the dual. Possibly I've got these around the other way, but that's once that's this inner product, the first or second factor. So that's the Fock space of the dual. All right, can anyone think of another operator on Hilbert space between 0 and 1? We have the identity and we have 0. Split the difference, half. By the way, these are all easily checked in the one-dimensional example, and you get some intuition in that. So if A is equal to 1/2, we did the calculation in that 2x2 matrix case. We would find that remember, let me just say this: in the C case, if H is equal to C, then CAR is the 2x2 matrices, and in this case, the phi sub A is the trace. Maybe normalized so that the trace of the identity is equal to 1. Okay? So that goes through to the infinite dimensional case. It's also a trace. There's only one because it's this 2x2, 2 to the n. There's only one such trace. It is the trace, and it has the property that in this case there is no kernel to that form. It's positive definite. All right? So that's sort of how it goes. We have 0, we have 1, and the representation, I should say that in these cases the representation is irreducible. both of these cases. In this case here, it's highly non-reducible because the whole algebra is also acting on the other side. It's a bimodule. So we get a lot of operators that commute with the left multiplication. Okay. So there we are. Oh, one more example. I'll try to interest you in this one abstract nonsense example by a little tease. You may ask, well, when is this representation of the CAR algebra? When is it irreducible? Irreducibility is one of those big words in representation theory. When is it irreducible? And the answer is pi sub a, I think I've called it, is irreducible if and only if a is a projection, i.e. a squared equals a squared equals a, projection. So in this example, it certainly works. 0 is a projection, 1 is a projection, but the half is certainly not a projection. So in that case, it's not irreducible. So if we want irreducible examples, we want to have projections, P, and projections we're going to call P. Fantastic. Pi is irreducible if and only as a projection. Yeah, and the little tease that I wanted, it's just something that occurred to me when I was talking about. At some point I said that when we close things up in this topology of pointwise convergence on a Hilbert space, strange things may go on in this limit. And one of the strange things is that if you take all projections, just projections, and you take the closure, you get all matrices, all operators between 0 and 1. Doesn't happen in the finite dimensions. It's kind of bizarre. It's actually the so-called weak topology. If you take all projections on a Hilbert space, so that's orthogonal projections onto subspaces, take the weak closure, don't have to add or anything, just take that set and take its closure, you get all operators between 0 and 1. Okay, so somehow projections we can expect projections to be playing a fundamental role in this picture. All right, so now I'm going to become more concrete. Everything's going to get more and more concrete. While, oh no, it's not. Sorry about that. I have something to add. We haven't taken. Oh yeah, we haven't done the physics magic yet. We haven't seen that. We have to see that. I'm going to go on until at least 15:15 today. You stay here and listen to this because this is you should all know about this. So. So let's let's do a little bit of physics now, and suppose that we had a H on the pre-quantized space. H is a self-adjoint operator. Okay? And I'm going to let P, I'm going to take this, remember, at this stage, to do my CAR maneuver, I'm looking to do it with projections, and then I'll end up with these nice irreducible representations at the end. So P is going to be the projection onto the positive spectrum of A, the spectral projection of H for H onto R plus union 0. So in other words, I'm going to take, if you like, if H happens to be diagonalizable, I'm going to take all of the positive eigenvalues, non-negative eigenvalues, eigenvectors, and see what space they span, project onto that. All right? And now I'm going to say the following. I'm going to do all of this junk that I just did, and I'm going to end up with a Hilbert space HP, which I didn't say here, did I? I said that P was the same as irreducible, but I should say if we have a P, then H it sort of combines the thing that's dual. Lambda of PH tensor lambda of 1 minus PH dual. Okay, this is quite compatible with the two previous ones. If you have, well, maybe the dual, I don't know. Up to the usual story about bar going. The HP, the second quantized fermionic Hilbert space, is the exterior is the Fock space on P of H tensor the Fock space, the anti-Fock space on 1 minus P of H. So what happens here is that on HP, so there's a two-step, sorry this is a little bit complicated, but it's extremely important. What's the role of these Hamiltonians in the first quantized Hilbert space? They give you time evolutions. So we're looking at e to the IHT. Okay? E to the IHT obviously commutes with p, which means that the Bogol-U, this automorphisms, which did I write them down as Bog? Maybe I hope I did. E to the IHT. This is the functor. Every time you have a unitary on Hilbert space, you get an automorphism of the CAR algebra. These preserve the inner product, P, given by the projection. Therefore, by abstract nonsense, they give you a one-parameter unitary group, capital UT, on HP. Okay, they're automorphisms. They preserve this inner product, so they go straight to the Hilbert space. They give you UT, and by Stone's theorem, UT, capital UT, is, we reverse it, e to the IT capital H, some other H. This is on the second quantized Hilbert space. So we've taken a Hamiltonian. This is the incredible, this is just mind-blowing how this works. We've taken a Hamiltonian on the pre-quantized Hilbert space, which may have its spectrum all over the place, and this was the problem for Dirac, because when he wrote down his Dirac equation, the Hamiltonian was just some nice first-order thing, and therefore it had to have spectrum, negative eigenvalues, positive eigenvalues all over the place. But then he did this in different language, and what's happened is that the H on the pre-quantized Hilbert space has become functorially this big H on the second quantized Hilbert space, and because of this, getting the lambda of pH and then the dual of 1 minus pH, all of those negative eigenvalues have switched around and become positive. So this is the miracle. This is the Dirac C. This is turning, what you don't like in physics. In physics, remember, energy has to be positive. And because of the first-order nature of the Dirac thing, we had negative energy and we couldn't avoid it. But by doing the second quantization, we functorially converted all the negative eigenvalues of the operator into positive eigenvalues, and the spectrum of H, this is the lesson, sigma of H is contained in R plus union 0. Okay? So this is a mathematical statement of this fantastic consequence of, if you want to impose, if you wanted to join quantum mechanics and relativity, then relativity a la Dirac says that the Hamiltonian is first order and therefore has this big spectrum, positive and negative. But then if you consider infinite families, large families, infinite families of particles with this fermionic second quantization, all of a sudden you can turn all of that negative energy into positive energy, and you get something that satisfies the properties of quantum mechanics on the second quantized Hilbert space. Energy has become positive. Okay, this is the mathematical statement of it, and it's, as mathematics, it's as rigorous and as elementary as you could ask for. Okay, so I have to head towards the end now. So that involves, oh shit, I still got to, I still got a bit more abstract nonsense to do. Okay, so let's review this, what we did with P and e to the IHT. And see, the main ingredient here was that if we had a unitary that commuted with P, it was canonically became a unitary on the second quantized Hilbert space just by functoriality. But what if it doesn't commute with P? So we're going to consider the situation. We have, remember, so we go back to the first quantized Hilbert space. We've got our projection, okay, and we've got a unitary. So we saw, in this case, what we used was if U commutes with P, then there exists a capital U on HP by functoriality. Well, there's a version that what happens is that this is certainly not true. You can't do this if it doesn't commute with P. However, if it almost commutes with P, if UP is what's called a Hilbert-Schmidt operator, then there exists capital U on, this is capital U, on HP with the property that U, A of F if you like, U star equals A of little uf. This is a nice way of saying it. So this is a result due to a whole lot of people in about the 1950s and 60s. I know Irving Siegel, I know David Shale, and I know Rideau, all responsible for this theorem in various guises. Okay, so let me say it once again. If we have a unitary on the Hilbert space which doesn't commute with P, but it commutes almost up to a Hilbert-Schmidt. Hilbert-Schmidt means that if you write it out as a big matrix with respect to an orthonormal basis, the elements are square summable. Take a basis, U becomes a matrix. Hilbert-Schmidt means, sorry, not U, but any operator becomes a matrix, and to say that the matrix entries add up in the L2 sense is the same thing as being Hilbert-Schmidt. So the theorem is, it's a nice theorem. It's not easy, but it's not, super deep. That if U commutes up to a Hilbert-Schmidt, then there is such a unitary. That in some sense, it's almost as if U acted. There was a canonical action of U on the second quantized Hilbert space. Well, how canonical is it? How many different U's can you get? Well, since it's irreducible, it's unique up to a scalar. Because this commute, any other one, blah, 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 they would have to commute with everything and therefore differ by a scalar. All right, so we deduce that if we define a group to be URES of H, so this is all unitaries such that UP is Hilbert-Schmidt, then we get a mapping from here to the projective unitary group of HP. This depends on P. So this is the final conclusion of the abstract nonsense ends here. We've had a lot of it, I apologize, but this is the end of it. Every time we have a projection on a Hilbert space, we have this so-called restricted unitary group, that's Graham Siegel's terminology, which is a set of all unitaries that commute up to a Hilbert-Schmidt with P. And we have, using our fermionic second quantization, got a projective unitary representation of that group. It's continuous also. So this is a projective unitary representation. Projective just means that it's a unitary representation, but the unitary is only defined up to a scalar. All right, example. Example. So now I've got to make the Hilbert space concrete, and I've got to make the projection concrete. And then once I do that, I'm going to have a mapping. So H is going to be L2 of S1 and SU2. Sorry, C2. I'm going to take L2 functions from the circle, two pairs of L2 functions from the circle, and P is going to be the Hardy space projection. So in other words, if you do Fourier series, there's the projection onto things that only have non-negative Fourier coefficients in their Fourier expansions. Or if you like, you can make it as if H is the rotation on the circle, sorry, H is actually I dd theta, then it's the projection onto the positive part of the spectrum. Positive spectrum. Okay, so that's an example. So we have therefore a mapping from U-res onto the projective unitary group of the corresponding Hilbert space. But what's in U-res? Okay, to make everything concrete, I've got to give you some goddamn thing in U-res. Okay, so this is what I've sort of been aiming at altogether. So here's a fact, and it's a trivial computation, matrix computation. If F from S1 to SU2, I could say U2 if I wanted to, is C infinity, then multiplication by F is in U-res. All right, so let me say that again because this combines sort of everything we've been saying. If I take a smooth function from the circle to SU2, that's called a loop, then MF multiplication by F acts on this Hilbert space, right? If I have a function from an L2 function from S1 to C2 and I have a smooth function from the circle to SU2, then I can apply the group elements to the vectors and I get a unitary. So this unitary is in U-res. So therefore, by our abstract nonsense, by this beautiful piece of abstract nonsense, we get a projective representation of LSU2. So this is the group of loops, smooth loops, to the projective unitary group of HP. Okay, so this is what Siegel calls the fundamental representation. By tinkering with it, namely by taking tensor powers, we get more representations from L of SU2 projective to the projective unitary group of HP tensor to the L. And L is called what's called the level of the representation. And it's a fact that the collection of unitary projective representations that you get in this way are all the possible ones such that there's this positive spectrum going around. All right. So I'm aiming very directly at the end of the talk now, but I have to say a couple more things. I haven't got the subfactor yet. So let's summarize what we've got so far. We've got this Hilbert space HP gotten by fermionic second quantization of just an ordinary L2 space, and then every loop on the circle, if we have a function from the circle to SU2, then we've got a unitary operator, UF, U loop. They're acting on this Hilbert space in a way that gives a unitary representation up to a phase. Okay. Now I'm going to divide the circle up into two intervals. So those of you who were at Alberto's talk yesterday will be very happy with this. We've got this band-limited situation here. So we're taking these sort of band-limited loops which have their support in I. So I'm going to call Li of G to be the loops, this is obvious notation, loops supported in I. So on I complement, they're equal to the identity. All right. And I've got to give this unitary representation a name. Let me just call it pi, forget all the stuff that went into it. It was really only P went into it. And what I can do is I can look at pi of Li of G. And then I can look at the von Neumann algebra that it generates. Well, my friends, that is a factor. First theorem in the business, this is a factor. All right? to end my talk, I have to give you a subfactor. So I'm now going to give you a subfactor. And that's going to be the following. Now I can apply the same thing, and Alberta will like this. This is a bimodule that's going on. I can apply the same thing to LIC of G. And the notation for this is standard in the trade. We just put two things. This means the von Neumann algebra generated by the group. So let's look at these. Loops in I obviously commute with loops in I complement. Okay? So therefore, this algebra commutes with this one. Therefore, actually that's... Anyone see what the problem with that is? These group elements commute with these ones, and I asserted that this one has to commute with them. Well, it's a projective representation, okay? It's a projective representation. So just because the groups commute doesn't mean that their images commute. But because SU2 is simply connected, it's okay. This is where I use SU2 rather than U2. So therefore, it's true. So I get that this algebra, which is a factor, is sitting inside the so-called commutant of this one. And this is notation, the commutant. And the commutant of a factor is a factor. So commutant means all operators that commute with it. So this is a subfactor. So, and it's been constructed as it's an algebra of bounded operators on the Hilbert space. And Wassermann's theorem says, Wassermann, among many other things, that this subfactor is the same as what I would have got in the first part of the talk if I had taken the invariant of planar networks being the Jones polynomial. But not just the Jones polynomial at any value, the Jones polynomial at a specific value, and that specific value is the one that Witten said that he could calculate by quantum field theory, and it's e to the 2 pi I of L plus 2, where L is the level, this guy here. Okay? So most of you will probably be very relieved to know that that's the end of today's story. I've come full circle. I have, by going in a completely different direction, and I haven't really said what this has to do with conformal field theory, but you probably know if you know what the term means. I have gone in a completely different direction. I have constructed, in an honest, completely rigorous mathematical way, a subfactor on a Hilbert space, and I've said that that subfactor, the theorem is that that is the same in some pretty honest sense as the one that we got from this combinatorial thing of invariant of planar networks using the Jones polynomial as the invariant, and the value of the Jones polynomial is the one for which Witten's Chern-Simons theory works, and none other. So that's the end of what I have to say. I apologize for going over, but there's a lot to say.
Thank you very much. Comments?
Circle with the left and the right. Would you put the two here instead? Does it really matter that it should be the one-dimensional circle?
Right. Well, you will remember that at the end of your talk yesterday, Raimundo said to you that the West-Zumino-Witten model was actually a separation of variables into left and right. Mm-hmm. Well, what I've constructed here is 1/2. This is the left move. There's left movers and right movers, right? This is the left or the right. I don't know. Mm-hmm. That depending on that inner product, right? You get left or right. This is 1/2. So you've done the separation of variables and you've solved the problem on 1/2 of it. Mm-hmm. And the sphere is the thing on which the whole thing is sitting.
I see. Okay. Thank you.
More or less.
comments? Questions? Please.
This is very nice procedure how you formalize this second quantization process. And then coming to the practical point, when we compute scattering amplitudes, essentially we need to compute traces of the operators, which reduces to the Feynman procedure. Does it help in some sense?
No, I don't think so. It's, I don't think so. It creates a little part of the theory which is completely rigorous, but whether it really helps with calculating scattering amplitudes, probably not. That's sort of, in some sense, way in the future, because that's not so rigorous, right?
Exactly. That's
yeah. So this is a rigorization of a part of the theory. It's intimately related to what I was going to say in the last 10 minutes of the talk about the Haag-Kastler nets for Neumann algebras. And one of the attempts to make quantum field theory rigorous, Haag and Kastler said that you should associate to certain regions of space-time algebras of operators on Hilbert space. Well, space-time has come down to be just this circle. This is both space and time. And the regions, and the nice regions, are just these intervals. And the Haag-Kastler algebra observables associated with A of I is precisely this von Neumann algebra generated by the loop group. And that theory satisfies all of the axioms of Haag-Kastler. And so, therefore, it should, that approach to quantum field theory is perfectly, in some sense, this is a constructive quantum field theory. And that is constructed. But, whether there's other approaches, for instance, Graham Siegel has a bunch of axioms for conformal field theory, and whether they are all completely satisfied is not entirely clear. A student of mine, James Tenner, that's sort of his thesis, but he hasn't got there yet. He's got almost there. And, of course, other people would say they have constructions, but I claim that if you want honest Hilbert space, as a mathematician understands Hilbert space, it hasn't been done. So, but it should come out of this theory. I think that we're starting to understand exactly the ingredients. And I should mention again the name of Anthony Wasserman, who really, this work started off as a joint project with him, and then it got too hard for me, so I sort of pulled out, and he went on and did all of the hard work and finished it off, and what I think is a real tour de force. Yeah, Raymond.
Please.
Is there a Wasserman theorem for other models, like say Virasoro, for example? Do you have what the Vaughan Jones side is?
Yeah. So one of the bones of contention, shall I say, between the mathematicians and the mathematical physicists even, are what has been done and what hasn't been done. And the only person who has any real right to assert that something has been done is Anthony himself, because all the subsequent stuff, when you really boil down to it, uses his work. So what has been done is Virasoro. So to do Virasoro, you need the observation that not only the loop group but the diffeomorphisms commute up to a Hilbert-Schmidt with the projection onto the Hardy space projection. And you can go ahead, and the local algebras are diffeomorphisms supported in an interval, and you get the same thing. And he has calculated, or he with his student have calculated what the subfactor is, and it's sort of an SU2 tensor. It's well understood. But then you could say, well, what about simply for other Lie groups? So what about for G equals? Well, he did in his seminal paper. He did SUN. Okay, and then Valerio Toledano, his student, did the orthogonal groups and possibly the symplectic groups. I'm not entirely sure about that. But to my knowledge, G2 has not been done, for instance. So, But unfortunately, everyone expects G2 to go just the same way, and what the answer should be is known. So people tend to just assume that it's been done and assert the results. In the von Neumann algebras in the WZW theory for G2, people will say, well, has it been done? And now there's a most unfortunate and very sad thing that has happened recently, and this is that Wasserman, not only did he lose his job, so he's looking for a job, and he's an extremely deserving mathematician, but he had in his office a whole lot of papers in which he'd done the case of a general compact Lie group, according to him. And this material was destroyed because he didn't have a job, he didn't show up in his office. The chairman of his department came in and destroyed all of his papers. So not only is he out of a job, but he's done all this exceptionally good work and it's gone. So he has to. It's very sad. And there's also the super conformal and so on. He knows how to do all of that as well.
Okay.
Yes or no? Yes, of course. If it's okay. Vaughan, two questions actually, but one is you cut the circle in two parts, and somehow this is too symmetric. Is it possible to kind of do it in two different, three parts, let's say? Does it make much of a difference? So,
oh, yeah, that's interesting. So I thought you were going to go in another direction, so let me go in the other direction first for you. So what was going on yesterday was we had this Fourier transform, and we cut that as well.
Yes,
well,
that's what I meant. Yeah, that's.
No, okay. Well, that's one question. So there's two good questions. One is that question. Well, that's exactly what we did, because what is the Fourier? What's the Fourier dual? Well, it's Fourier because of compact. That's Fourier series.
Yeah.
And what was our basic projection that we were working with? It was a Hardy space projection, which cut out 1/2 of the Fourier series. Mm-hmm. So that's exactly what we've done here. Now, your other question, which you actually said, is what if we cut it up into more intervals? And here, 3 is not terribly interesting, but you can cut it up into 4 intervals.
Okay.
And you can take the von Neumann algebra associated with these two, and then that will commute with the von Neumann algebra associated with these two, and you'll get another subfactor.
Uh-huh.
Okay? Well, this is what is known as the Drinfeld center or the quantum double or whatever of the original one. So this was worked out as a formalism. It's relatively soft compared to the Wasserman thing, but it's true that if you do that, you somehow magically get this so-called Drinfeld center, and the fusion rules become abelian, and all kinds of nice things happen in that. If you take 4 intervals.
Okay, maybe it's time to thank again Vaughan Jones. You saw how much interest your lectures presented to the people.
It's a fascinating topic.
I hope you enjoyed talking to us.
Absolutely, it's been a wonderful time.
Okay.
Thank you once again for the invitation.
Thank you very much.
Cool.